Welcome back from the coffee break. So I would like to share now the information on how we have transferred this kind of methodology to a more complex environment at higher pressures, where our resolution, of course, was not sufficient to resolve the smallest scale. So the idea as well here is, by looking into the flame displacement speed, better understanding what kind of cyclic variations take place. But this is restricted to the early phase of flame propagation, where you still have a chance to observe the propagating flame kernel using this kind of OH-LIF imaging in two adjacent planes. So identical as before, but now the region of interest has been located around the spark plug in this dual plane OH-LIF approach, again using two independent UV lasers. But in this case, that has been not a high-speed, continuous high-speed laser, but we have used for each of the plane a double pulse YAG laser in combination with a dye laser, such that we have had only two instances from which we could deduce the overall flame speed. Similar as in the other experiment, the stereo PIV has been placed here in between, and the distance between these parallel planes has been aligned very carefully with different distances. One of them was 0.5 millimeters. So you see then, after post-processing, the location shown in red and blue corresponding to this color coding here of these two OH planes in that field of view, and in between you see then here the in-plane velocity shown as vectors and the out-of-plane velocity given as colors. So a rather complex experiment in terms of the aligning, where all of these three beams are fed through this Bowditch piston, and were then directed against the cylinder head with this viewing plane shown over here. And here in the bottom you see the arrangement of the cameras. In addition to the CL camera looking through the bottom here, there is the two stereo PIV cameras, similar as in the atmospheric condition setup. And you see here the two OH LIF cameras equipped with image intensifiers. There is not much more room left for more cameras. As you see, that comes as well to a natural limit. If you would like to now measure maybe a third, a fifth plane or whatever, it becomes really critical how to arrange these cameras, even if you have, let's say, the budget to buy them. And then I like this view graph very much. You see actually what's happening with very high resolution that was achieved. Around the spark plug you see here the one realization of a flame at one instant with certain resolution resolved these two planes, and in between the stereo PIV. The same as we have seen before. I don't have to go into detail. I think the only thing I should really stretch during this explanation is the convection velocity has been taken 0.4 millimeters in front of that flame front. That's very important. You have to do that. If you don't do that, you would need to know the density at the location of flow field measurement. And the density, of course, is a quantity that is very difficult to measure in such an engine. We have seen you can do that in principle by Rayleigh imaging, but then you would need the cross-section as well, as you would have to overcome the problem with any surface reflections in an engine that is with Rayleigh not easy. So the only chance we have seen was to determine therefore the convection velocity 0.4 millimeter in front of that white line over here. And then the rest is the same idea, the same data post-processing to achieve then here the turbulent flame speed, which is for this realization in this small fragment here, in this small volume element, shown here to vary again in a certain range, including as well negative displacement speeds. Interesting is as well to visualize how the orientation is. Now you see here a certain orientation showing only the flame displacement speed. Now you switch the angle of observation and look along this parallel light sheets, and then you see well, the direction of this flame displacement speed along with the length of that vector in this projection, and compare that with the same viewing angle, but for the convection that is of course totally different. And then as well, if you go along that line and plot the convection as well, the modulus of the displacement speed, you find as well, of course, things which are completely uncorrelated as expected. Okay. And you see as well here the negative ST values that shoot down to certain values in this realization smaller than -2 meters per second. From that, you can now, or repeating that experiment, using in that case 80 cycles again, you can build up a histogram here normalized and showing a PDF with a wide spread of velocities in this engine for this operation conditions between -5 and 15 meters per second with a mean value of 2.5 meters per second and a precision I'm going to talk about in a second that we estimate with a 1 sigma to be in the order of 1.5 meters per second. So if you, for the moment, accept that precision to be discussed in a second, then it becomes obvious, even if you're with this limited precision, this negative and contains still, or must be real. And in high pressure environments, as well high turbulence levels, of course, you have a much stronger wrinkling, and our resolution by far will not have been sufficient to resolve all these small structures. As well, it has to be pointed out that at high pressures, this kind of instability is listed here. Hydrodynamic instabilities, thermal diffusive instabilities become more important. They're much stronger than at atmospheric conditions, and thereby as well we have a contribution that wrinkles the flame. It's not only the turbulence, but as well these kind of instabilities wrinkling that flame, such that you in the end need to account for when you model that with an appropriate turbulent flame speed. So when I've seen that first, I was as well asking the question, how reliable is that? And so at least partly I will discuss here what we have done to convince ourselves that the error, the noise, the precision is not the main reason for this negative end over here. So if you do this kind of imaging, being not really volumetric, but still by these adjacent planes, of course, there could be some out-of-plane transport that causes the effect over here. And so that is visualized over here. Assume a flame kernel like that with a strong out-of-plane direction, which is called here W. Then you would as well have, let's say, an impact of such a structure on the observed displacement speed. And so you can try to analyze this effect by excluding strong out-of-plane velocity magnitudes, and as well exclude strong or large angles. And then using the same data, but by this condition exclude a certain amount of data, for example, that are outside a certain range of angle between convection and displacement, or as well exclude a certain range that's difficult to read, taking only those out-of-plane velocity realizations with lower than 2 meters per second, which is rather low. Then you find histograms or PDFs that look rather similar. So you see by that, although you have maybe reduced the data that has been analyzed to only less than 50%, with this conditioning the same, then you build up trust, okay, that must be real. Or changing the distance between these planes, yeah? This delta Z over here. It's quite an effort to do that because you have it's a big alignment, and you have to redo all the experiments and then the processing. And that has been done here starting from 0.5 to 0.25 or enlarging to 0.75. And you see the effect is existent, but the overall message about this negative ends still holds true. Or here, using a different field or interrogation box sizes for the PIV as well has a certain impact relative to your case starting with, I think, larger PIV interrogation volumes. You see there is a certain impact, but still you find this negative end. So it's maybe not perfectly precise and accurate, but the main message still holds true. We have estimated by a Siemens star the resolution of the OH-LIF cameras. Yeah, that is the Siemens star is like the Air Force target, a structure that you put in the plane and then look which structures still are resolvable. So quite impressive, 80 microns, not bad. Then we did some error propagation, including the stereo PIV, and then came up with that. We have a 1 sigma standard deviation of 1.5 meters per second. And the maximum here, let's say for 3 sigma, is 3 meters per second. And I go back 3 meters per second, that would not, even if you account for this worst case, would not remove that negative end in the PDF. So that must be true. And so, of course, we tried to do similar things that people have done with the DNS data and try to correlate that with high positive curvature, try to correlate that with high compressive and tangential strain, and as well looked into the sensitivity of the ISO level using as well different distances where the PIV has been taken for. But for a reason which is still not clear yet, we couldn't find the same results as for the DNS because they have found some correlations to these quantities, which I understand, but in the experiment we couldn't find that. So, and it was interesting to see that this was true in the engine. That was as well true for the open configuration I've shown before, and as well from other publication shown here as well. They couldn't find that. They have done a very similar experiment and came to the same conclusion. So still, what I think holds true, the negative end can be only explained if you have a change of the flame structure when you have these two instants. And just a second. And that must be due to transport effects that, of course, we cannot resolve. And that's why here we come to a clear limitation of the experiment. Yeah, high pressure, complex environment, difficult turbulent structures. Although we have a huge experimental effort, there is no real chance really to understand in the end what's going on. That is my belief, that if you want to resolve that now more, we have to find people doing that with highly resolved simulations. And then combine that, make sure that the simulations are really comparable to what we are seeing, and then use the simulations to get a better insight into what's going on, and using this highly resolved simulations then for model development for the coarser simulations used in industry. And that is a long effort, but we come to that point because there's a group, for example, in ETH in Zurich, they use DNS in engines with real sizes. Yeah, it's not a small box anymore. Yeah, this is a 80 millimeter or something like that bore, and hopefully in future we can cooperate with these people in Zurich from Konstantinos Boulochos to have as well a chance to look into these combined approach, experiment and DNS to come up with a better understanding. Okay, your question, please.
So your flame front is determined by the location of the OH. Tracking the OH. Does the DNS specifically follow the OH also?
Yeah, the question is whether the flame front tracking in the DNS is identical to the experiment. Actually, I don't remember exactly how they determined the flame front there. It will, of course, depend on the quantity. If you take maybe the maximum heat release rate, which is in DNS easily accessible, of course, they could use as well the OH, but why using such a strange quantity if you have much better? And then I don't know for that pressure, but we have looked into that in atmospheric conditions for methane air flames, equivalence ratio number 1. That was only 30-40 microns. It is still compared to the displacement where you take the velocity data, maybe only 1/10. And have you higher pressures, then the distance, because everything gets so steep and small and even thinner, then this distance will decrease and is maybe then below the resolution limit we anyway have. Yes?
So, maybe you already said it, but did you check if this negative end changed when you took the velocities at further isosurfaces away from
Yes,
the OH?
very good question. The question is whether that PDF changes when you're, let's say, instead of taking the velocity 0.4 millimeters, take it at 0.5 or 0.6. Yes, we have checked that. You find a change in the PDF, similarly as with the other parameters, but the negative end stays. Yep. It's, of course, a very obvious thing that you should better check. Okay. Any further questions? Yeah.
What's the light sheet thickness?
The light sheet thickness, don't remember exactly. I have to refer back to that publication. We try to make it very thin. It might have been in the order of 150 microns, but I'm not sure anymore. Maybe better look that up. It was published somewhere. I think it was in this Proceedings of Combustion Institute 2015. First author Brian Peterson. Okay. Now, yeah.
So another question about just mention that there's a new technology, CH-PLIF, with a combination of PIV. So I think it can also be used for this purpose.
The question or the comment was that there exists as well the possibility to use CH-PLIF instead of OH-PLIF that as well then can be combined with PIV. Of course, that's doable. The problem with CH-PLIF is you have much worse signals. Yeah, you have much worse signals. Dependent, of course, of the excitation scheme, you have two possibilities, exciting around 390 or 430, but anyhow, your signal level is much lower. And that for CH.
CX band, 310 nanometer.
Pardon? CH?
Yeah, CX excitation.
Ah, CX excitation. Oh, I'm not aware of that one. The CX is okay. Okay. It's a pretty new. I don't know that. Maybe you sent me the article. Okay. Okay. All right. We are limited because only 2 planes, and so in the last symposium there have been contributions showing that you can do better, and of course there are a number of groups being interested in that to do it tomographically. With the same arguments as before, because it's 3D phenomena, it would be, of course, great if you would have a better resolution, what we call out of plane, the 3rd dimension somehow included. And we have here a first attempt to use that methodology for tomographic OH fluorescence. And so you see the experimental effort is now shifted more to the detection side, because in principle now you can use a single laser with sufficient pulse energies. You create here a volume that is observed by a number of cameras. In that case, there was we had with cooperation LaVision and Göttingen access to 4 intensified cameras, which are shown here. This would have been first CCD cameras, and to enlarge the number of projections, there have been used as well image doublers, such that you have had 8 simultaneous views. Looking at this transition, like always, that typically is used, the XA transition here from V equals 0 to 1 using a Q1 8 line. And so this laser was operated with 20 millijoule, which is not a very large number for a YAG pump dye laser, and that was used to view a 3 by 3 by 3 centimeters volume. And then using a very simple flame, only for demonstration purposes, and using an algorithm that has been developed by LaVision, not by us, based on this simultaneous multiplicative algebraic reconstruction, SMART called, and in that case using 100 iterations in this reconstruction. You find here as well some times that you need for processing. It takes minutes for one volume to be reconstructed if you go for high resolution, and if you release your resolution, then it takes remarkably less time. And then after reconstruction, of course, you can slice by slice look into the OH distribution. Nothing has been corrected here, so not yet any correction of laser absorption, no correction of laser intensities, so only the raw data that have been processed by this algorithm. And you can see now these results, where you see, of course, some, depending on where you are more or less, some blurring because of that reconstruction. Yeah? You would expect in this Bunsen flame there is no OH in the center, but only OH in regions where you have, of course, passing the flame front hot gases, and then no OH outside in the co-flow. But you see as well the reconstruction is, although you can imagine where the flame front is, there is as well some blurring over here. You can now, in a different view graph, using TechPlot, for example, visualize 1/2 of that flame, although the whole flame has been imaged. As a next step, you should, of course, convince yourself that the reconstruction is not too far from what you would obtain with 2D PLIF. And that's why we have done a comparison with 2D PLIF in the identical flame, and then here using the center plane and using a certain location, a certain intersecting line shown over here, which was here selected 4 millimeters downstream the nozzle, and using only 1/2 of that to compare the images reconstructed from tomographic PLIF with the two-dimensional OH PLIF. And the blue one is shown here with the TLIF, with having really the full volume of 30 millimeters illuminated, and that's the blue line that can be seen over here. And then that is compared with PLIF 2D. The sheet size or thickness was, I think, 200 microns, and this is this red line. And you see the gradient here of the 2D is steeper than that with the tomographic. Now, to get an idea about the corresponding resolution, the spatial resolution has been released in the 2D PLIF by applying linear filters with different mask size spanning from 3x3 to 9x9 millimeters. And then you can see that with the 5x5 millimeter, that is here the green line, you can at least for the high intensities, you can reconstruct the tomo PAV reasonably well. So you get an idea about the corresponding resolution you would have in PLIF when doing this reconstruction with 30 millimeters illumination. Of course, that depends as well on the depth. If you, for example, not use a full 30 millimeters in the out-of-plane direction, but reduce that stepwise over 10 to 4 to 2 millimeters, which is roughly a factor of 10 larger than the PLIF, then you find here rather similar reconstructions when you make this volume a bit thinner. That's, of course, expected. It does have an influence. Yeah? But anyhow, the structural size seems to be captured quite well, and this is shown over here. If you now take the average of many of these shots and take, after normalization, take the profile's width at 50% with a certain mean and variance value, you find rather similar values for the TLIF reconstructed images with a 30 millimeters depth in illumination. So you would say it's not so bad. With that, at least large structures can be resolved. And that is, of course, very nice to see what you can do with that. Here you see the outer contour. You can now look for different slices. Here's a slice cut off at the center line, where you see here these flame. Now it's a turbulent lifted flame again. Sorry, I didn't mention that. With nominal reconstruction volumes of 75 cubed microns. The Reynolds number 5000, the identical flame that we have seen before. And you can look for parallel horizontal cross-sections or vertical cross-sections. And by that, at least the idea is to look for the larger structures and later on combine that with somehow a volumetric flow field measurement. That is something that needs to be still done, but that's ongoing research. So you can say method development. Okay, and very recently, just finished a couple of days before I came over here, we expanded that as well to high speed, where we used the facility looking in autoignition. So this is a huge experimental setup where you have here a co-flow which is heated. In that case, up to it can be heated up to 1350 Kelvin, in which you inject fuel. Right now it's still gaseous fuel, but it can be as well later on particles like coal or sprays or so. But then you will have a lifted flame, but the interesting region is actually over here between the nozzle and the lifted flame base where you have autoignition. Yeah? And then the reconstruction is working really nicely, and although we didn't have so much pulse energy as in the low speed, we're now talking about a conventional high-speed dye laser, frequency doubled to 283, pumped by a normal high-speed YAG laser. I think that has been operated with 80 watts per 80 watts, and with 6 millijoule at 532, with only 200 microjoules at 283, with a laser volume cross-section here in this area, and 8 views with these cameras, and then it's only starting. You would see here these autoignition kernels shooting up. Further downstream there would be the lifted flame base, and you see now how these kernels in time and space. Yeah, of course you would like to have it even faster and so on, but that is at least a development that is ongoing. And I have to admit that is as well like being a small kid. Playing with that is as well very nice, although maybe at least in the beginning the combustion process is only a vehicle, but at some stage of course you need to transfer that kind of information and something that can be used for better understanding of these combustion devices. Yeah, that needs the fun period sometimes is then over. Okay, are there any questions?
Could you briefly touch upon any significant challenges about extending this to 2-line to do tomographic thermometry?
The question is extending that approach to 2-line thermometry. In principle, it's doable. Yeah, I think yes, it's doable. But of course, it's a factor of 2 larger experimental effort. By equipment and by aligning and everything working simultaneously together, it is more than a factor of 2. Yeah, it's like being a father. From 1 to 2 children, it's not only a factor of 2. I can tell you. Yes.
Have you looked into absorption of laser energy in probe volume and variations in the laser volume intensity?
So the question is whether we have considered the absorption losses, for example, at the excitation, but as well at the emission. Yeah, the emission as well is done redshifted around 310, where you have at 308 the 0-0 transition, at 313 the 1-1 transition, and the 0-0 of course as well reabsorption. Depending on the case, it can be really severe. No, in this kind of experiments we have not yet done that, but it should be considered in one of the next steps, because it will have, of course, it will change the result. With this high-speed imaging here of these flame kernels, it's not so important because the flame kernels are rather small. If we go for larger flames, then of course increasingly it becomes important. Okay. Then we can leave that part. And finally, we can use the remaining time to make use of the techniques that I've been showing and presenting over the week to you. And here the goal is not only to repeat one or the other technique, but as well to show how to make use of it. But in the end, really, the intention of all these diagnostic efforts must be to better understand certain phenomena in combustion system. That's why we're here. That is what we are paid for. And as I've shown on Monday, my belief is as well to increase stepwise the complexity. Yeah? We started many years ago with open atmospheric turbulent flames, and then added complexity. Added complexity like in the previous example with autoignition. But here adding complexity is by looking into the interaction between flames and walls. That is for any practical combustion device of critical importance. And it's really astonishing that it has not been considered too much, at least in the combustion community. There has been some efforts, especially in France, looking into that, but there the primary intention was the heat transfer. And we have to go beyond that, and my intention is to share some recent results about that in this lecture series. So I will give you a more sound motivation why the interaction between flames and walls is of importance. And then I will as well show you how we approach that. And you will see that flame-wall interaction is divided into different classes that are called head-on quenching, where a flame is approaching, for example, like in IC engines, initially at least, a wall before it's quenched. So the propagation is against the wall, whereas in sidewall quenching, the idea is if you have a wall like that, the flame is creeping or moving along that surface. It's not always easy to distinguish these extreme and idealized cases. And so you will see here flame dynamics as well as some idea about thermochemical states going clearly beyond only heat transfer. And the sidewall quenching, which is now preferred by my side to investigate, we will see how you can make use of this kind of imaging to come up with a mean reaction rate deduced from that data. That is a very important quantity in modeling, and it's nice to see how you can use the data to extract that information. But maybe even more important to have a closer look into thermochemical states, like in Raman-Rayleigh spectroscopy, where I've shown you that in the full beauty. This is here restricted then only to measurement of temperature and one very important species, which will be CO. Okay, so coming to the motivation. Flame wall interaction is really topical, not only since recently, but it dates back 200 years. By that time, a lamp was patented to be used by miners underground. They didn't have electricity by that time regularly, and so they needed to have an illumination without any ignition. And having here a nice lamp operated non-premixed, you do have this candlelight atmosphere. But of course, if there would be any gases outgassing from your mine, you would have an explosion. And so by that time, using a mesh allowed to transmit the photons, but worked as a flame arrestor. So even if there is a surrounding of ignitable methane air or whatever it was, there was a certain protection against that because the flame from the inner could not pass through that grid. Okay, safety technology. Then some years back, people were excited about gas turbine combustion in combination with catalysis. So catalytically assisted combustion, where you find here that is from a group in Switzerland in Paul Scherrer Institute, where they have looked into that catalytically assisted combustion. Of course, everything happens here at the surface or close to the surface. Microcombustion. You see here a Swiss roll combustor taking from that review article from Maruta in 2007, where of course a lot of the phenomena are linked to the interaction between the gaseous phase and the wall. Very important. Modern gas turbine combustors operated overall lean to get low NOx levels. You see here a photograph of our combustor, where you typically, that is true as well for others, have a wide spreading angle over here, such that you have the flame with its heat release partly interacting with the wall and the effusion cooling. And I think we have no time for today to go into detail, but it's very interesting to study, especially here, the interaction of the flame and the flow with not only the plate from which you have the effusion cooling, but as well with these tiny little jets coming out of the effusion cooling. So that's really a very complex problem, and that cannot be handled by simulations yet. such that we need experimental evidence what's going on over here. And the gas turbine industry, they have not a detailed idea what's going on. That is, in the end, empirical. And to overcome that, you need experiments looking into this level of detail. And of course, combustion engines, because of downsizing, because of cold start, that is maybe the most critical time where you have strong interactions between flames and walls. And so for those of you who are not familiar with that problem, the most important properties are shown over here. We speak of flame wall interaction when the flame has come as close as a few flame thicknesses. Yeah? Then the flame starts to sense the wall. Then you have an intense coupling. And of course, the most prominent thing is the heat transfer. And that can be huge. Yeah? For hydrocarbon-based fuels like methane, at 1 atmosphere, you have up to a megawatt per square meter. That's a huge impact upon, of course, the chemical kinetics. And such that the flame is then quenched, and that means you have incomplete combustion. If you have incomplete combustion, then you have unburned hydrocarbons, and you're oxidizing the CO not completely to CO2, and that is, as I said, specifically important for cold start engine conditions where as well the three-way catalyst may not have been ready for operation. So that makes up a lot of the emissions that we still have in the IC engines. So maybe you cannot avoid any wall in an IC engine, of course, but a better understanding might help for better modeling, and then in the end as well for engine concepts that may reduce that. And so that is visualized over here. The problem, you do have flame temperatures which are significantly larger than the wall temperatures in IC engines. We have seen that by the previous chapters. We have measured that with thermographic phosphorus. We know they are below 700 K. So you have here up to 2,000 or nearly 2,000 K difference. Which means in addition to that heat losses, you have radical recombination reactions leading to flame quenching, incomplete combustion, and as well, in addition to the pollutant formation, that heat losses are severe, causing losses in engine efficiency. And so 30%, that's an estimation based on a review article by Alkidas, whereas here from the PEX paper 18 years back, where this author has looked into different publications and came up with a good estimate of, by that time, 30% losses in the engine by heat transfer through the walls in the cylinder, and roughly 40% of the unburned hydrocarbons due to flame wall interactions, but as well including crevices. Yeah? That's included over here. And so that is visualized by this simple experiment where we have seen that before, where you have these evaporating fuel meat droplets to visualize the flame propagation. And now we're not interested in the early phase as before, but we're interested when the flame touches the wall now. And so this has been as well presented earlier this week, where we have measured upon the approaching flame the heating of the piston surface. I just want to remind you here, there is a paper that has been as well recently published. But what we are now doing is, instead of continuing that research in the engine, as I said earlier, try to do, when you have a little understanding of the problem, not directly go into the complex geometry, do it with simplified geometries which are motivated by the real one. And the motivation comes here from the early phase of flame wall impact, where you have head-on quenching. I explained that, where the flame ideally in that concept is propagating just perpendicularly against the wall, or sidewall quenching where it creeps along the wall. Of course, you as well then have quenching the crevices, which needs then a different setup, which I will not detail today. So we will have a closer look into head-on and sidewall quenching. And that has been, as I said, of course, investigated for a long time, but not as intense as you would have expected. Maybe because of the problems, both experimentally and numerically and theoretically. It's not so easy approach that. From the experiment, really, you have to resolve, or you should try to resolve, the boundary layers of the velocity, of the temperature, and the species. So you need high resolution. And so it's wise not to go directly into high pressure environments where all the scales are even smaller, but stay maybe with lower pressures initially. What has been done? So here, these authors are all from France. So there, in the 90s, there was a big interest in that country in these kind of flows, where you have had a constant volume combustion chambers with ignition and then filled pre-mixed fuel air, and looked in different geometries where the flame then approached against the wall. We have done that differently because what I dislike in these concepts is you have to charge them, ignite, take your measurements, evacuate, fill it again, takes long. And that's why we have done an experiment including some convection. You have simply a nozzle, as you will see, from which you issue a pre-mixed fuel-air mixture. You ignite that with a laser, and then the flame propagates against that wall. Yeah. Or in sidewall quenching, again, people have done that in constant volume devices, or here in systems where you have a flame holder which was then giving rise to a laminar flame, which was then interacting with the wall, which is typically, of course, conditioned, so temperature controlled, or like Dani SQD has done first, using here a system where you can have as well a turbulent flow. You do have here simply a V flame. You take a flame holder like a ceramic rod, shown here in a cut. Then you have one branch of that V flame which is not interacting with the wall, and the other is doing that. And I think this is a very nice setup, because depending on the flow rates, you can as well have a difference in the mean angle of interaction. And so that is as well a device which is, I think, very, very useful. So here you see what's going on. That is taken from a 1D simulation from Johannes Janneke's group that is under conditions without any convection. You see here a spatial coordinate for the top and the top left and the two bottom graphs. Here you see the location of the flame front over time. So maybe I guide you through. Initially there is coming the freely propagating flame. Let's wait for it until it comes back. Here it comes. Now eventually it starts to sense the wall. The CO2 source term is going down. That means now the chemical activity is going down until it's extinguished when we have reached zero. And then it's not the flame anymore that bounces back. Do you have an idea what that is? It is extinguished after that time. And so the temperature profile is influenced now by the wall. It's getting flatter, and now it's off. The flame is off. Why is that happening? It is doing what?
You're dropping below the ignition temperature.
It's dropping below ignition temperature, of course. That's why the CO2 source term goes to zero. The flame is extinguished. But what happens then? What is the dynamics coming from afterwards? Why is that profile doing a flattening? Any idea? Pardon me? Conduction? Yes, that's it. It's a diffusion process. It's a diffusion process, heat diffusion. And that means by this diffusion, of course, to the wall, then you have a flattening. Yeah? And then that is initially stagnant mixture. So there's no convection implied here. And here on this chart, you see it travels with a constant flame speed until it comes close to the wall. It starts to sense the wall somewhere now, and then it's decelerated, and then this bouncing back is to molecular diffusion processes. So that is the simplest case you can think of, 1D, and without any convection, and of course without any turbulence. Yes?
Do you have shock wave?
Do we have shock waves? In this here, no. There's no, the pressure is nearly uniform here. It's slightly different, of course, in the exhaust, but there is no shock wave involved. No. Okay, so that has been analyzed by, for example, Thierry Ponceau at Cerfrax in Toulouse with a paper Combustion of Flame 93, where he identified, based on such simulations by that time with simplified chemistry, the flame approach that is shown here in phase number 1. What you see here is the flame power. The flame power is not yet disturbed. Then you do have here as well a constant flame speed. Then we have the second phase of quenching, where the source term of CO2 from the previous slide the chemical activity goes to 0, but that comes along not only with the deceleration of the flame speed, it comes along as well with the heat flux, which is here normalized with the flame power. The flame power is calculated like here. And then we have the third phase, the post-quenching period, where you then have only transport effects, giving rise to that back bouncing over here. And still, of course, some heat conduction to the wall. Okay, very interesting already, but more important is as well then for the real combustion systems to include turbulence. And so I mentioned that Dany Escudé came up with the idea to have here a flame holder. The approaching flow is now turbulent, and this gives rise to a V-flame, a turbulent V-flame, and one of the branches is then interacting with this wall. In that case, it was a ceramic plate. And this is now visualized for 3 instantaneous snapshots, again with a simple me imaging, having aerosols in the turbulent mixture over here, and then look for the vanishing me scattering, giving rise to an idea where the flame front is. And then from that you can deduce you do have an impact on the flame brush. It is reduced and the wrinkling is changed. And that needs to be investigated now more detailed, and people have done that or classified that. This is taken from a textbook by Poinceau and Denis Venant, where you have an interaction between flame and turbulence, like in those flames we have looked at earlier, where the flame modifies turbulence and the turbulence wrinkles the flame. We do have now, in addition, interaction between, let's say, turbulence in the wall. The turbulence changes friction and heat transfer to the wall. And the wall modifies, of course, length scales. Everything is getting thinner and smaller, and as well by shear forces creates turbulence. And we have the interaction between flame and wall, where the flame heats the wall and the wall quenches the flame. So a very complex interplay. In the past, we have looked primarily in flame turbulence interaction. Now we look into flame turbulence wall interaction. And that has been done primarily by people from the DNS side. And here are some authors listed, initially starting only with simplified chemistry, very simple chemistry, but then more recently, Andrea Gruber working with Jackie Chen at Sandia, or Christos Fousakis working with Konstantinos Bolochos at ETH Zurich. They have used then as well complex chemistry in their DNS approach. And I reviewed that recently in a paper published in the PCI 2 years ago. But there is a lack of experimental data. That is really what is missing. And these quantitative data are really needed to better understand these strong interactions. And that means in the end you have to analyze boundary layers, try to get a good resolution in space and of course in time. And not only looking into flame structures, that is very important of course, but as well looking into thermochemical states. And maybe I just briefly introduce the experimental approach before I think we need another break. So I said that we have the classification into head-on quenching and sidewall quenching. And here you see the animation from head-on quenching. We have just taken that nozzle, operated with methane air premixed, surrounded by the co-flow, just taking 1/2 of that opposed jet burner. Yeah, reuse these devices to a certain extent. And you can put in a turbulence grid if you wish, or operated laminar. Yeah? And then ignite that with a laser as shown here, and then the flame propagates, extinguishes, and you have to repeat that. It's transient, and that's why it's not so good in terms of statistics. And of course, when it's laminar and you restrict yourself to the center line, it's 1D. But typically a low sample number, because you have to, you maybe can do 1 experiment per second. And if you want to do good statistics with point techniques, that takes ages. That's one really advantage of the sidewall quenching burner. It operates statistically stationary. Of course, it's 3D. And however, because of that, you can achieve a higher sample number because you don't have to wait for all the time between ignition, propagation, quenching, waiting that everything is again to what it was before, and then repeat the experiment. Here you can do it faster. And that is these 2 experiments. Both are based on this kind of contracting nozzles. I haven't detailed that previously. These contracting nozzles are intended to provide a top head flow coming out of that nozzle. And then you can insert a turbulence generating plate or not. And then you create here a propagating flame that is then traveling or approaching the wall. And here you see typical configurations. We have mostly done the experiments with 5,000 Reynolds number. Without the grid, without this turbulence generating grid, it was laminar, although 5,000, very smooth everything. Inserting the grid, you could increase the turbulence level to something like 6 to 7%. Or using a similar setup over here, where then you have here in the out of plane direction, the rod stabilizing the flame and then the interaction over here. And the intention is then, of course, looking initially at quenching distances. You want to visualize the flame close to the wall, but you want to know the wall temperature, you want to know the heat flux, you want to know the velocity boundary layer, you want to know the reaction rates near the walls, you want to understand the thermochemistry going on when the flame is quenched, meaning you have to measure thermal boundary layers as well as concentration boundary layers. And that's maybe a good point where we can stop and then have a closer look into these things by using techniques that we have discussed during the week. Okay, so maybe we can restart at 11:15, then we have 1 hour left for the remaining topics. Thank you.